Welcome to Notes 2.2 and 4. Today we're going to talk about deductive reasoning. So if you remember last class we talked about inductive reasoning, which was using a pattern to come up with a conjecture. And so today we're talking about deductive reasoning, and let's see if we can figure out what deductive reasoning is over the course of these notes today. So we're going to begin by talking about a conditional statement. By the way, just a little note-taking tip. There is a lot of writing in today's notes, and I am not going to slow down. So you're probably going to want to pause the video in order to be able to write down everything that I write down today. Good luck. All right, conditional statement. A conditional statement is a logical statement that has two parts, a hypothesis and a conclusion. The hypothesis begins with the if, and the conclusion begins with then. So you will sometimes hear me call this an if-then statement. But I'm always talking about conditional statements. So here's an example. If you do your homework consistently, then you will get a better grade in geometry. So the hypothesis part is considered the if part of the conditional. So if we underline it once, it's the you do your homework consistently part. The conclusion would be the then part of the conditional, which we're going to underline twice. You will get a better grade in geometry. I'm not guaranteeing you a good grade, just better than you would have gotten if you don't do your homework consistently. Although the nice thing about conditional statements is they don't have to be true. They just have to be if and then. We'll talk about whether or not they're true in just a second. All right, so here's an example of a conditional statement. If a quadrilateral has 4 right angles, then it is a square. And remember I said we talk about whether something is true or not. Well, we call that truth value. And truth value is the extent to which a proposition is true. And there are only 2 values, true or false. That's what I like about math. There's no maybe, but what about, there's no gray area. True or false. And in this case, if a quadrilateral has 4 right angles, then it is a square. What is that? Is that true or false? All right. It is false. The reason why it's false is because I can come up with a counterexample. What's the counterexample? All right. It is a rectangle. A rectangle meets the first part. It's a quadrilateral with 4 right angles, but it's not a square. And then you're going to go into discussion, but Mrs. Uken, squares are rectangles. Yes, all squares are rectangles, but not all rectangles are squares. So let's just table that for right now. All right. And then we have a converse. A converse is where the hypothesis and the conclusion are switched. So for example, in this statement up here, the converse would be if a quadrilateral is a square, then it has 4 right angles, right? I've flipped the 4 right angles and the square parts, okay? And if both the conditional and the converse, so both the original statement and the flipped statement are true, then we can write a statement called a biconditional, okay? A biconditional has a very distinctive form. In the middle of the biconditional, you will see this phrase, if and only if. And that's how you recognize a biconditional. But remember, it's got to meet the criteria that both the conditional and the converse are true. We will try to make you write one for something that does not have this met, and you better believe that you better not do it. All right, so here's another conditional statement. If a triangle is a right triangle, then it contains one 90-degree angle. Is that true or false? Okay, it is true. That's what makes a triangle a right triangle, the fact that it contains one 90-degree angle. So the converse of that would be where I flip-flop my if and my then. So my converse would be if a triangle contains one 90-degree angle, then it is a right triangle. Is that true or false? Well, that is also true. All right, so now I have both a conditional and a converse that are true, so I can write a biconditional statement. And in the biconditional statement, I get rid of the if and then, and I stick if and only if in the middle. So a triangle is a right triangle if and only if it contains one 90-degree angle. So if and then are gone. I stick if and only if in the middle, and I go back to my conditional statement and put it in that order, although because they're both true, it really doesn't matter which order it goes in, but we like to go back to the original conditional statement. So there are a couple more statements to talk about. The first one is a negation, and a negation occurs when not is added to both the hypothesis and the conclusion. Or if it's just a simple statement, you just add not to it. So for example, it is hot outside. The negation would be it is not hot outside. Although I'm recording this in the summer, and I can tell you right now, it is very hot outside. All right. It isn't humid. Well, we wouldn't stick it isn't not humid. All right. Double negatives, no good. So we would say that it is humid. A double negative makes a positive. That's what your mother's been telling you all this time, right? Okay, and then our next statement is going to be the inverse. So in the inverse of a conditional statement, we are going to negate the original conditional. So whatever that if then is, we are going to add not to that. And then the contrapositive of a conditional statement, it negates the converse. So when we flipped the if and the then, that's the one we would negate this time with the contrapositive. Now all of these statements can get a little confusing, and you know how I like patterns. So find an empty spot somewhere in your notes and write this pattern down. If we have these statements, that original conditional, that is my if-then, right, my original if-then statement. Let's put it this way. Let's call it if X, then Y. Well, my converse flip-flops the if-then. So my converse would be if Y, then X. My inverse was the negation of the conditional. So it takes the form if not X, then not Y. And my contrapositive was the negation of the converse. And my contrapositive would therefore say if not Y, then not X. And then that biconditional that we talked about, it's a special statement that I can only write if both of these are true. Let's write some statements. So here's my original conditional statement. If a polygon has 3 sides, then it is a triangle. How do we feel about that? True or false? Well, it's obviously true. So let's talk about its converse. The converse, I'm flip-flopping the if and the then. So my converse should read, if a polygon is a triangle, then it has 3 sides. How are we feeling about that one? Well, that one is also clearly obviously true. If both my conditional and my converse are true, then I am able to write a biconditional. Biconditional is the one that has if and only if in the middle. So a polygon is a triangle if and only if it has 3 sides. And notice in this one, we stuck the if and only if in the middle of the converse because the order doesn't really matter because both of these are true. All right, my inverse is the negation of the original conditional statement. So I'm going to go ahead and stick not in here. So if a polygon does not have 3 sides, then it is not a triangle. How about that one? True or false? Well, that's also true. In order to be a triangle, you have to have 3 sides. So if you don't have 3 sides, then you are not a triangle. And then finally, my contrapositive is the negation of the converse. So we're going to go ahead and stick not in there. If a polygon is not a triangle, then it does not have 3 sides. And again, that is true. You'll find that this pattern, if you put these statements in this order, tend to either be all true, all false, or true, false, false, true, or false, true, true, false. They don't alternate. Just something interesting I noticed over my many years. At the beginning of this lesson, I told you that we were going to talk about deductive reasoning, and then we proceeded to not talk about it at all because we were doing all those conditional statements. But we were really using deductive reasoning, particularly when we were coming up with the truth value of those statements because deductive reasoning uses facts, definitions, accepted properties, and the laws of logic to form a logical argument or conclusion. And when we were saying, things about triangles or squares, we needed to know what the definition of a triangle or a square was, what the properties were, in order to go ahead and come up with the conclusion as to whether or not those were true or false. And believe it or not, even though you've just barely scratched the surface of geometry, you actually know a lot. I like to think of deductive reasoning as how many tools do I have in my toolbox that I can apply to a problem. Well, we've got a fair amount of tools already tucked into that toolbox. For example, we know a bunch of stuff about points, lines, and planes. We know that through any 2 points, there is exactly one line. And it's important that it's phrased like that, not just one line, exactly one line. And therefore, if it's a line, it must contain at least 2 points. We know if 2 lines intersect, then their intersection is a point. And we know that through any 3 non-collinear points, there exists exactly one plane. Therefore, a plane must contain at least 3 non-collinear points. If 2 points lie in a plane, then the line containing them must also lie in that plane. And if 2 planes intersect, then their intersection is a line. Now, all of these postulates are going to be tested on the vocabulary quiz for this unit, and it's important that they are phrased exactly like this, exactly one line, at least 2 points, at least 3 non-collinear points. Okay, don't get close, be precise. Let's talk about a few more properties. Here's one of related lines. I've got M parallel to N and N parallel to K. Then my conclusion should be that M is parallel to K. Right? That's my transitive property going on there basically. And is this always true? So if I have line M, terrible line, and line N and line K, if these 2 are parallel and these 2 are parallel, then are these 2 always parallel? Yes. I can't think of a counterexample. Can you think of a counterexample? If you can, tell me tomorrow. All right, let's talk about perpendicular lines. So I've got H is perpendicular to L and H is perpendicular to F. So what do you think is true? All right, well, if you told me that L is parallel to F, I can understand why you said that. So we've got line H here. All right, and it is perpendicular, so it's perpendicular to line L, and it is perpendicular to line F, and therefore these 2 lines are parallel to each other. All right, well, in this situation that I've drawn, that is exactly right. These 2 are parallel. But there's something critical missing here to make it always true. And what's missing is in a plane. For example, if I don't see these words, then I'm not limited to a single plane, which is what my diagram shows, a single plane. Think about the corner of a room. If the edge where the ceiling and the wall meets, right, that edge, that's a line, and it is perpendicular to where the 2 walls meet. Well, the place where the 2 walls meet is also perpendicular to the other wall and the ceiling. And yet, the first wall in the ceiling and the second wall in the ceiling, those aren't parallel to each other, right? Those are also perpendicular to each other. So it's not always true. The corner of a room is a counterexample. Back to interpreting a diagram. When we talked about this before, we said that there were certain things you were allowed to conclude from a diagram, and then there were other things that you definitely could not say based on a diagram. If your justification was because it looks like it, then you are so very wrong. So remember this, you can only assume information about size or measure, so the lengths of segments or the measure of angles, if it's marked on the diagram. So no matter what it looks like, you must specifically see congruency markings or right angle markings. All right, so we can assume that all points shown are coplanar. We're clearly shown plane P here. All of these points are in plane P. I'm not showing anything otherwise, so I can go ahead and I can go with that. All right, and then as far as linear pairs go, well, BHD here and DHF, for example, those are definitely a linear pair. They're adjacent and their opposite sides form, or their non-common sides form opposite rays. All right, and then BHD and FHA are vertical angles. All right, their sides form two pairs of opposite rays. And then AHJ, which is this point right here, the intersection of those two lines, and H is this point right here, and D, those are all on the same line, therefore they are all collinear. And I know that AD and BF intersect at point H, because it's clearly shown on the diagram. Here's what I can't assume. I can't assume, no matter how much GF and E look like if I drew a line through it, that they would be on the same line. I cannot assume that they are collinear unless I physically see the line. Now 2 points, any 2 points, whether I see a line through them or not, so BE here, that would be collinear because through any 2 points there's exactly one line. So by definition, any 2 points are collinear, but not 3 points. All right, and I can't assume that BF and CE either intersect or do not intersect. It looks like if they were to continue out here on the plane that they would intersect, but I don't actually know whether or not they're parallel, so I can make no assumptions whatsoever. And I can't assume anything about congruent angles or perpendicular angles or the measure of any angles, whether it be 90 degrees or acute or obtuse. Nothing about angle measure can I assume. All right, so here I have another diagram. This one actually shows 2 planes intersecting, and we need to check and see whether we can make following statements based on this diagram. Let's see, E, D, and C, are they collinear? Yes, they are clearly shown on the same line, so we are good to go there. And then can we assume that BD, so this line right here, and EC, can we assume that they intersect at point D? Yes, that is also clearly shown. All right, do I know whether these are perpendicular? No. Do I know whether anything is perpendicular? Not unless I see that little box that indicates a right angle. So no, nothing about any type of measure or length can I assume. All right, well, this concludes part 2, and I will see you in class. Thanks.